Hi everyone, thanks for joining us. I'm just going to give it another minute or two just to give more people a chance to sign in and then we'll get underway. Hello everyone, thanks for joining us. My name's Gemma Shackleton. I'm the marketing manager for METROSIL, a range of silicon carbide varistors manufactured by M&I Materials in Manchester, UK. I'll be your host for today. That means that as well as introducing and closing the webinar, I have the important task of clicking through the slides and making sure that things run nice and smoothly. So as you know, today we'll be talking about METROSIL varistors and how they provide superior quench protection. We'll be comparing them to other energy extraction devices, and we'll have a case study session that illustrates some real-life results courtesy of CERN when it comes to METROSIL performance. Before I introduce you to today's speakers, I'll just quickly go through some housekeeping rules. Firstly, anyone who's dialed in by telephone, if you haven't done so already, please just make sure that your microphone's muted. We'll be taking questions at the end of the session, which will be in about 20 minutes' time. You can submit questions to us at any point during the webinar. To do this, just open the chat window. If you click the red arrow in the top right-hand corner of your screen, that will open up a chat box, and in there you can enter your question, and then at the end of the session I'll go through as many as I can and I'll put them to our presenters. So now that I've quickly covered some housekeeping rules, let's get on to introducing today's speakers. So I've already told you my job title, but to tell you a little bit more about me, I've been looking after the METROSIL brand for 2.5 years now. When it comes to marketing, my background is predominantly in engineering, and I have to say that in my experience to date, METROSIL is one of, if not the most exciting products that I've worked with, especially when you take the brand's history and current activities into account, which we'll cover shortly. And moving on to Dom. So Dominic Cole is our commercial manager for METROSIL. He looks after our relay and current transformer customers when it comes to overvoltage protection, and he's headed up our superconducting business over the last 2 years or so. Dr. Tom Galvin is our materials scientist for METROSIL. Prior to joining us, he studied structural carbide materials for the nuclear industry as part of his PhD, and he's also produced a master sintering curve and analysed impedance data for METROSIL on behalf of the University of Sheffield. In terms of quench protection, Tom has been heavily involved with analysing our extraction data alongside CERN, which brings me nicely onto our next speaker, who we're extremely pleased to have on board. Glyn Kirby is a senior engineer at CERN. He's responsible for designing and building superconducting magnets. METROSIL has been working with Glyn since 2018, and it's anticipated that our varistors will make it into CERN's Large Hadron Collider. I won't go into too much detail now, because Glyn will tell you more about this shortly, but instead, I'll pass you on to Dom, who can get the webinar underway by introducing you to M&I Materials, the manufacturer behind METROSIL.
Okay, thanks for that, Gemma. For those of you that don't know us, I'd like to just give a little background into M&I Materials, if I may. In total, M&I Materials currently have 5 major brands. And in research labs, nuclear medicine and accelerators, it's possible to find almost all our specialist materials being used. Today's webinar concentrates mainly on, and solely on METROSIL silicon carbide varistors and the benefits of using them as a fast energy extraction device and a useful replacement for a linear dump resistor. So a bit of background. M&I takes its name from the Micanite and Insulator Company, originally formed in 1901. From this grew Metropolitan Vickers, a large UK manufacturing and research company in Trafford Park, Manchester. So at Metrovix, Apiazon, a specialist vacuum grease and oil diffusion vacuum pump, was discovered and used as part of Cockcroft and Walton's accelerator to split the atom. In 1937, Dr. Sillers, part of the research team and an insulation specialist, discovered silicon carbide varistors and branded them Metro after Metrovix and Sil after silicon carbide. By 1940, hundreds of thousands of METROSILs were being manufactured for surge protection in the national grid. Fast forward then to 2008. By this time, millions of METROSILs are in service worldwide. In China, they installed METROSIL on the world's largest 22 gigawatt hydropower plant. And then innovation continues then at Trafford Park, and METROSIL commissions a high energy test lab that enables us to subject our units to their full ratings. So let's move on a bit to discuss METROSIL in more detail. So over the years, METROSILs have become synonymous with electrical network protection, and as such, METROSIL appears in many IEEE recommended practices and standards. For example, 421.6, that's a recommended practice for the protection of synchronous machines. C5713 is an instrument transformer protection standard. DLT 843-2010 is a Chinese power industry standard that mandates the use of critical protection. METROSIL also appears in many technical publications, including the recent Power Generator Reference Book by Professor Ji-Cheng Li, shown on the right there. METROSIL is used to protect all of the world's largest power generation plants, and some of our many reference sites include the Itapu hydro plant on the border of Brazil and Paraguay. In the US, we protect the Hoover, Grand Coulee, Chief Joseph, the John Day Dam, Salem, Peach Bottom nuclear sites. In Europe, METROSIL protects hydro dams across Norway and all 59 EDF power plants, nuclear power plants across France. As mentioned, from its beginnings, METROSIL saw use as an effective and robust overvoltage protection and energy extraction device. So for large salient pole generators, you'll find METROSIL switched in across the field windings under de-excitation, clamping the back EMF LDIDT and extracting the energy and protecting the coils of these very expensive machines. And this application lends itself nicely to superconducting magnet coils during an unexpected quench to replace the dump resistor. So how does METROSIL actually work? For this, I'll let Tom explain. Over to you, Tom.
Thanks, Dom. So METROSIL is a composite ceramic varistor material that relies on silicon carbide, a wide bandgap semiconductor. The silicon carbide, which is held in a ceramic binder, along with some additives to fine-tune the properties, acts a bit like an array of randomly oriented PN diodes or switches. With increasing voltage, these switches change from a highly resistive to a highly conductive state. As more junctions switch, the current flow increases exponentially with a linear increase in voltage, which discharges energy quickly due to the high power, while keeping the voltage at a safe and acceptable level. The next slide shows this a bit more clearly. So METROSIL varistors do not have a fixed resistance, and so do not follow Ohm's law. This is what we mean when we say they're non-linear resistors. Instead, we use this equation, V equals C times I to the power of beta, where C and beta are characteristic parameters of the METROSIL. C is the voltage across the varistor at 1 amp. Beta is the non-linearity coefficient. And for our high energy disks, this value is typically around 0.39. This means that the voltage across a METROSIL is proportional to the magnitude of the current rather than the current itself. Typically for our high energy disks, the current would have to more than quadruple to double the voltage across the disks. This means we can actually clamp the voltages at higher currents, while also squashing the tail end of a discharge when the current is lower. Based on the composition and the geometry of the disks, as well as how we connect them electrically, METROSIL assemblies can be tailored to meet any voltage, current or energy requirement. For example, our largest installation on the Three Gorges Dam is designed to absorb hundreds of megajoules of energy reliably. Now I'd like to show you the equation we use to model inductive discharge through a METROSIL. There's no need to write this down. We can send a copy to you by email if you're interested. Just let us know in the chat window on the side. The maximum voltage here is determined by the magnet being protected, and then achieved through the type of METROSIL used in its configuration. The beta in this equation, as I mentioned in the last slide, is typically around 0.39. Due to the nonlinear VI relationship, a small increase in voltage results in a much faster discharge time. So we really want to take the maximum voltage up as high as the magnet will safely allow to really speed up that discharge. We use this equation to model resistive coils, but to apply it to a quenching superconducting coil, RF, which is the DC resistance of the coil, would be a time-dependent value for the whole magnet as it quenches. And this is obviously magnet-specific. The coil inductance as well could be a time or current-dependent function, and again, that's down to the individual magnets. So using that equation, here's some simulated data which shows a varistor against its equivalent linear resistor, by which I mean that they both have the same maximum voltage at the start current. You can see the METROSIL discharges the current more quickly than the linear. This can be up to about 3 times quicker, which reduces the overall time the coil is actually energized. So this is simulated data, but in fact, thanks to CERN, we have some real data of a METROSIL protecting a superconducting magnet. So these tests were performed in collaboration with CERN on one of Glyn Kirby's short model CCT magnets, which he'll talk about in more detail shortly. Here you can see the METROSIL go up against a 0.7 ohm linear dump resistor during a quench. Not only is the current discharged a lot faster, but the sum of the I squared T's, which is representative of the energy discharged within the coil, is a lot lower when a METROSIL is used. I've talked for quite a while there, so I'll hand you back over to Dom now, who'll talk a bit more about our process and our testing regime in-house.
Okay, so if we break our manufacturing process down into simple stages, we can demonstrate the difference that manufacturing makes when it comes to critical protection. So first we mix silicon carbide with a ceramic binder and some additives, and we tune the recipe to meet customer requirements. Then the discs are pressed and sintered at high temperatures, and the faces are metallized to form the electrodes. There's also a 2-pack painting and curing process to form an insulated disc edge. And all of that is a fairly typical manufacturing process, but what sets us apart, however, are the next couple of steps. We match METROSIL discs to tight specifications so that all the discs in a unit share the current and energy equally. This tight matching prevents some discs taking more than their share and improves the performance and longevity of the unit in the field. Our final stage is rigorous testing. So here I'd like to take a closer look at something very special and unique to METROSIL, HETL, our high energy test laboratory at Manchester. Now, this is a large controllable bank of ultracapacitors, and it has an internal energy storage capacity of around 10 megajoules, but we're able to discharge safely up to 2 megajoules of energy into a METROSIL unit to verify its performance. So if a customer tells us the maximum current and energy values and a protection voltage, we can demonstrate that a unit can handle this energy while keeping the voltage at or below a safe maximum. HETL's a calibrated system that produces accurate test waveforms and a valuable proof of performance. So our test and manufacturing processes are tightly quality controlled. We're both ISO and factory audited by OEMs, including ABB, GE, Siemens, and we've got a Class A supplier status for critical protection. So from testing, I'd like to move to a case study on superconducting magnet protection and introduce Glyn Kirby, Senior Magnet Designer at CERN. So over to you, Glyn.
Thank you, Dominic. My name's Glyn Kirby. I'm one of the lead engineers for the superconducting magnets at CERN. So 3 or 4 years ago, I met Dominic and the team from METROSIL at one of CERN's introductions to industry events. And at first, I didn't understand quite what METROSILs or the Varistors did. But after a while, I realized that this could be extremely useful for the superconducting magnet protection. It really can move forward the design and performance of the magnets. At the moment, CERN is involved in a major upgrade where they're replacing several kilometers of magnets either side of the 2 main experiments. And several of these families of magnets have energy extraction systems. And at CERN, we like to use new technology, although, as it turns out, METROSIL is not a new technology at all. It's been, as Dominic explained, it's been used widely. So what could METROSIL do for us? Well, it can affect the protection of the circuit in 2 ways. We can reduce the hotspots, which of course is very advantageous for superconducting magnets. And also we can reduce voltages. So depending on the setup that you choose, you can adjust for the 2. And over the last 2 or 3 years, we've published several papers on the development that's gone on at CERN for METROSIL, and we're hoping to introduce METROSIL into some of these new magnet circuits. You see Dominic and myself here in the SM18 CERN test lab a couple of years ago during one of the first sets of tests. Next slide, please, Gemma. So the basic circuit is identical to any normal energy extraction system, with voltage taps looking for a magnet quenching, which will then decide to open a switch and extract the energy from the magnet into an external dump. This has 2 advantages. One is it reduces the hotspots of the magnet, and it stops heat load into the helium. On the 2 circuits below, on the left you see just a classical coil dump resistor with a switch in parallel. And of course, for this type of system, it turns out that the resistance times the voltage gives you the voltage to ground. Now, of course, sometimes we need to extract more energy, which would mean more voltage. So in this particular case, the voltage for the circuit in the CERN power supply was limited. So we used 2 matched METROSILs, putting earth in the center and so we could extract twice the energy and yet still maintain the voltage to ground for that. On the right hand side you see a photograph of the two METROSIL units. They were just connected via copper braids to the positions, the terminals where we would have connected the normal dump resistor. Next slide please, Gemma. So we've now tested METROSIL on a number of different magnets, and we're in the process of optimizing this to minimize, well, to control the hotspot temperatures within the magnet to around a maximum of 200 Kelvin, and also reduce the voltage to ground. And you can see on this larger plot on the left hand side, the x-axis is operating current, and the vertical axes are both resistance on the left hand side and voltage on the right. The blue angled dotted line is the performance of the resistor, and the red curved line is the METROSIL. We can see at 400 amps the voltage to ground is considerably reduced. In this case it's about 30%. This test data was taken from magnets which are being built and tested in China, as China are giving CERN a present of a set of superconducting magnets. But they have also taken on to use the METROSIL in part of their test facility. On the right hand side at the bottom graph, the x-axis is current and the y-axis is a quench integral. You could also think of this as hotspot temperatures, with the dotted line being our target maximum value. You can see the string of small green triangles. These were resistor values, and the bottom values would be the equivalent Varistor or METROSILs, which Tom mentioned earlier. And you can see there's a considerable reduction in the hotspot. So of course we can play with this. We can either have slightly more voltage and less hotspot, or vice versa. So this is, we're definitely seeing that this is a big advantage for superconducting magnets. And I'm really sure that in our community we will start seeing these used more and more. Next slide, please, Gemma. Okay, these are papers which we published over the last few years at 2 or 3 of the magnet conferences. And if you go to my ResearchGate project log for the CCT corrector magnet, you can download the papers and see all the day-by-day development that's been going on with this magnet and the use of METROSILs over the last 3 or 4 years. Next slide, please, Gemma. This is where I hand back to Tom and let him finish off the webinar. Thank you very much.
Great stuff. Yeah, thanks for that, Glyn. That's really good. So to summarise, METROSILs are high energy varistors that are extensively used in the power industry to protect against transient overvoltages and to provide a means to quickly extract energy from inductive loads. Benefits of METROSIL over linear resistors, namely the faster discharge, the lower energy discharge in the coil, and the overvoltage protection aspect, are all applicable to superconducting magnet discharge during an unexpected quench. Another advantage is that when METROSIL, the material, is subject to currents and energies well above its specified design limits, the material fails in a short circuit manner, so the coil is never subjected to high voltages or open circuit conditions. We have a great track record stringent QA testing requirements, which are audited by the OEMs we supply. Our 12,000 series Quench Protection units, which are shown here, can be specified to act as a direct replacement plug and play for existing dump resistors. We're always keen to work with labs or customers to help design and specify the correct METROSIL for your needs. Thank you for listening.
Okay, thanks Tom, Dom and Glyn. I've selected 3 questions here that have come in, so I'll get cracking and start with those. Chris has asked for some more information surrounding our high energy test laboratory. Tom, you might be the best person to help with this.
Yeah, okay. So the high energy test lab was originally commissioned just to give excitation customers more peace of mind, really. We tested the discs for their voltage and current relationships, but the question always was, can they handle the energy? And before HETL, to test that, you'd have to connect them to a generator. So with HETL, we hit every single unit that goes, any excitation or supercon unit that goes out. We can hit them with a voltage or current led square wave or an inductive discharge waveform to kind of simulate real discharge. Each unit sees the full energy of its rating, and every unit is supplied with a test certificate detailing the unit's performance. Again, just to demonstrate that we're up to the task. I hope that answers your question.
That's brilliant, thanks Tom. Dom, I'll put this one your way. Justin has said, these Varistor devices take a lot of energy. What temperature do they get to?
Yeah, that's a good question. Okay, thanks. Yeah, we design METROSIL units on the larger of either current or energy for a given clamping voltage, and we always keep the designs pretty conservative. And typically we wouldn't exceed 160 degrees above ambient. You could potentially force cool the units. That would drop that figure. There's an exponential cooling curve actually associated with the high energy units, which we can let you have. And also, just to say, there's an optional add-on energy monitor system which consists of some infrared sensing electronics, which can be retrofitted to METROSIL. And it provides a kind of condition monitoring system, which we can send details on that as well, if you're interested in that. Okay, hope that answers that one.
Brilliant, thanks Tom. Yeah, if anybody wants to know any more about the condition monitoring, just let us know in the chat box and we'll make sure that details get sent out to you. And finally, Glyn, I'll put this question your way. Robert has asked, how do you model the quenches with the Varistor?
Oh, that's a really good question. Inside a superconducting magnet, as it quenches, it's a bit like a fuse calculation, with the coil gradually becoming more and more resistive and heating up, and so some of the energy is dissipated in that. So then, as part of the circuit, you also model the characteristic of the METROSIL and put the two together. So this is normally you do this with the dump resistor, but then the formula that Tom gave you, you can use that to cover it as well. And of course, we're also interested in fast recovery to start operating the magnet again. So the METROSILs actually cool down quickly, so we can restart. And in China, they've been using this and they've repowered the magnet only a few minutes after a quench and extraction. So yeah, this is if you want to know more about the quench calculations, you can contact me directly and we can talk about that further if you like.
That's great, thanks Glyn. We're just about running out of time now, so I'll leave questions there. For those of you that didn't receive an answer to your question, don't worry, they've all come through, and we'll make sure that we come back to you directly. If you do think of something to ask, whether it be later today or even if it's next week, please feel free to take down our presenters' contact details and you can drop them a quick email. Don't forget as well to check out Glyn's blog on ResearchGate. If you need the link, again, just feel free to contact us and we'll make sure that you get the link sent through. I'd like to take this opportunity to thank you all for being with us today. We're covering a lot of time zones. I appreciate that it's very early and it's very late in the day for some of you. I'd also like to thank Glyn for joining us and presenting his data. Overall, we hope you found the session useful and informative. Myself, Dom and Tom will have met many of you at various superconducting events over the last 2 years. We hope to see you all again as soon as it's safe to do so. But until then, please stay safe and take care.